Alright, so I've got with me here my handy dandy plastic ruler that we can use to actually measure the lines that I have drawn here in order to get a sense of scale. You know what, heck, we'll use inches. The scientific community may condemn me, but we'll do something a bit gutsy today, why not? So this line is about 2.25 inches. That is the true dip, which once again we know because we know the direction of it. And the apparent dip, once again, is going to be, we'll call that 3.5 inches. Trying to keep the numbers relatively simple for the sake of this example. 3.5 inches. Now, this is an incredibly simple, it's really just a portion of a map, but let's just say that on this map the scale is 1 inch is equal to, I don't know, 500 meters. 500 meters horizontally. Okay, so we know that the true dip travels 2.25 inches, which is, let's see, 500 times 2.25, a quarter of 500 is 125, 1,125 meters horizontally, and the apparent dip excuse me, is 3.5 inches, which is 1,750 meters horizontally. And now what we can do with this is think about these, the true dip and the apparent dip as gradients, right? Since we have this, these contour lines that give us elevation, we know that these have changed by 200 meters. Both of them go up to the 300 meter contour line. So we can say that that's 200 meters divided by our two numbers. And then we can write these as gradients, which will be incredibly useful. So I'll just plug these into the calculator. 200 divided by 1,125 is equal to roughly 0.18, and 200 divided by 1,750 is equal to roughly 0.11. We're not being more precise, once again, simply for the sake of this example. Two significant figures should be good. Okay, now I'm going to clear some space here and keep our final gradient numbers, because here comes an equation. And this equation states that the tangent of the apparent dip, AP, is equal to the tangent of the true dip, TD, times the cosine of any angle, but we're going to call it beta. And what beta is it's the angle between these two. And, well, first of all, we don't know that. We're trying to find it in this example. But what it's useful for is in finding the angle of the true dip, because we can measure the direction and the angle of the apparent dip thanks to just using methods I discussed in my previous video regarding strike and dip. But we can't find the true dip, assuming that there's something obstructing our vision and causing us to read this apparent dip. So we can find the angle and the direction of the apparent dip, but we can only find the direction of the true dip because we know it's always perpendicular to the direction of strike. So if we want to find the actual angle of the the true dip, then the angle of the true dip is going to be equal to the angle of the apparent dip minus, or wait, no, it's going to be equal to the angle of the apparent dip plus the angle beta, because the apparent dip is always smaller. It's between 0 and the true dip. Okay, so this is just plugging stuff in now. The tangent of the apparent dip, so that's a tangent of 0.11. The tangent of the true dip, that's a tangent of 0.18, and then just multiply that by the cosine of beta. Okay, so plugging this into the calculator, the tangent of, actually we'll do one more step. The cosine of beta is equal to the tangent of 0.11 divided by the tangent of 0.18. So finally that gives us the cosine of beta is equal to tangent of 0.11 divided by the tangent of 0.18. The cosine of beta is equal to 0.611. So if we want to find the actual angle beta, then we get that beta is equal to beta is equal to 52.3 degrees. So that is the difference between our true dip and our apparent dip in their angles. So you could have previously found the angle of apparent dip simply by using the methods I discussed in the previous video. I'm not going to go through them again in this video. This was mostly to show you how to use apparent dip to find your angle of true dip, because in the real world there will be plenty of instances in which you can't tell the dip of strata simply by looking at it, whether that be due to a natural crossing of maybe a cliffside with some geologic strata, or due to the obstruction of man-made features such as roads or whatnot. But yeah, that's basically the process. I guess I'll give a quick rundown of everything to do, just because this is a relatively lengthy process, and we like simplifying things down. So the steps you're going to take exactly, just to review. So first and foremost, find your strike. Once again, strike is just a cardinal direction that is pointing in the direction that is pointing in the direction that the rock is clearly not dipping, to put it in its most simple terms. And then using your strike, find direction of true dip. Because true dip will always be perpendicular to your strike. And then third, you're going to not so much calculate, but rather just find your apparent dip both direction and angle, because you will be using the angle later on. And then fourth, either construct or use a previously existing profile of the area you're looking at, which means you're going to be using a contour map. Construct or use. Which, of course, if you're in a popular area for geologic profiling, then it shouldn't be hard to find one that already exists. If you're just in the middle of nowhere, just doing some sort of little test on the road outside your house, then you're probably not going to find one, and you may have to make your own by taking a few measurements of elevation and strike. So after you've constructed your contour map, measure your lines. And these lines are just following the dip gradient, or not the, excuse me, the dip direction, right? They're just following the dip direction across the map until you reach the end of that strata of interest. So once you've measured those, I'll put this in the same step, just calculate the gradients, which is once again just using the contours, the measurements of the contours divided by the measurements of the horizontal distance that the dip run. And then finally, once you have these gradients, plug them into the equation. Once again, that is the tangent of the apparent dip is equal to the tangent of the true dip multiplied by the cosine of beta. Put that in a nice little box. And then finally, having cosine of beta, well, technically take the inverse cosine of beta, or the inverse cosine of the cosine of beta in order to find beta. But once you have beta, just add angle beta to angle of apparent dip to find your angle of true dip. And that's it. With that, you have your strike, your direction and angle of your apparent dip, and your direction and angle of your true dip. It can be a lengthy process, and it does require different media of representing your geologic strata of interest, but hey, it's just another method of finding dip, and one that is much more accurate to the real world, especially in cases where the roads are create very large obstructions to the actual dip. So just keep that in mind. The lesson of this video, not everything is as it seems, and for that reason we have mathematical methods of finding the truth, the true dip. Guess I'm done blabbering for now. Hopefully this was informative, otherwise good review. Hope you guys enjoyed, and I will see y'all in the next video.